All right. So for today, now we are going to chapter 15. So about the power series and Taylor series. So you know what power series is. So well, because most of you have already attended the single variable calculus course, and the power series was one of the most important topics in the single variable calculus. Well, for the complex analysis, the power series is even more important than single variable calculus, because well later it turns out that every analytic function has on its own power Taylor series, and they are all in the power series. Sorry, every analytic function can be represented by some power series. That means they are always, as the name suggests, so all these analytic functions, they are analytic. Yeah, I'm repeating myself, but well, so do you remember the original definition of the analytic function? So a function is said to be analytic. Well, when you are in the real analysis or the calculus course, then if I say a function is analytic at some point, that means it has a Taylor series, and the Taylor series agrees to the original function as some non-zero radius of convergence. That was the original definition of the analytic function. But however, in complex analysis, we interchangeably use the complex differentiability and the analyticity. And that is because if your function is differentiable as not just a single point, but if your function is differentiable on some open neighborhood of the point, then that guarantees that the function has a power series, and the power series agrees to the original function in some non-zero radius of convergence. So this is what you're going to study at the later half of this course. Okay, so in order to do that, today I will need to introduce some basic definitions and notions and terminologies on the complex power series and the series. Okay, well, first I'm going to introduce the infinite series and infinite, sequence. Obviously, these numbers are all complex numbers. And has a limit. So this is defined by, definition is almost the same as we did in the calculus. So that means for any epsilon, so you should be able to find some integer n such that if n is, the index is greater than this n, then the difference between the z and the zn should be less than epsilon. And obviously, if this is the case, and then this is denoted by the limit n to the infinity, zn is tending to z. And if there is no such a limit point, if there is no such a limit, no, then we say the sequence diverges. Okay. And so as you can see from this definition, so the notion of converging sequence is exactly the same as we did in the calculus. So there should be no difference. But And the next theorem actually gives us more explicit idea, the relation between the real convergence and complex convergence. I mean, they are exactly the same thing. Suppose that I have a complex sequence. So I should be saying that the real part is xn and the imaginary part of is yn. And let me say the z is just x plus iy. Then this complex sequence is converging to z which is if and only if the real part is converging to the real part of the limit, and the imaginary part is converging to the imaginary part of the limit. So they are mathematically equivalent. So I will try to prove this, and if I can prove that, then that means, well, actually, we can actually enjoy this very nice equality. So I mean, limit is the operator limit turns out to be linear even in the world of complex numbers. So then, based on if you believe in the statement, then I can just say just like this. Oh, okay, right? Isn't that great? Yeah, I really like this, and also so. If you can, and this is when these two terms, well, in order to show that these two guys exist, then all I need to do is just a calculus 101, so single variable calculus. So that means, well, provided that I have this statement, then I can actually make use of many interesting facts and theorems from the calculus to the complex analysis. So yeah, I believe this is the one most important theorem for today's lecture. All right. So this is a two-sided statement. Well, which is easier? Yeah, I guess I will try to prove this side first. So since we are assuming that these two guys are converging to x and y, so I must be able to find two integers n1 and n2 such that if n is greater than n1, then x minus xn is less than, well, yeah, I should be saying that not epsilon, but epsilon over 2. And same thing is true for the difference between y and yn is less than epsilon over 2. So, well, this is very typical statement. Now, let me choose a greater number between n1 and n2, and I'm gonna call this guy n0. And for indices greater than n0, I have the difference between the z and zn should be, well, so z, well, what is my z? X plus iy, and zn is xn plus I times yn. So this is what? Yeah, x minus xn plus I times y minus yn. Okay, great. And because of the triangle inequality, I have, so this is bounded above by the x minus xn plus y minus yn. And since they are both less than or equals to epsilon over 2, so everything should be less than epsilon. Okay, great. What about the other side? Okay, so since we are assuming that this complex sequence is converging to this complex number, so for an epsilon, so I can find an integer n0 such that if the index is greater than epsilon, then z minus zn, well, in other words, x plus iy minus xn plus I times yn. So this guy should be less than epsilon. Okay. Okay. So from this inequality, so I must be able to show that these two convergences. Okay. So okay, let me try to think of the difference between the x and xn. Oh, yeah. Okay. So you know, the x and xn, these are all real numbers. So that means if I add another complex number over here, these are So this is an imaginary number, right? So real number and imaginary number. So this is, well, so you can consider this guy as the real part of this complex number. And by doing so, well, I have this nice inequality over here. And well, this is precisely the same as this expression over here, right? Am I? Yeah, good, right. So this is also less than epsilon. So, well, I can use the same trick for y minus yn. So y minus yn is also less than epsilon. So we are good. So yeah. So let me try a silly exercise. What do you think is the limit of this complex sequence? So -1 plus I times -1 to the nth power divided by n squared. This is a complex sequence, but you know, but there is nothing to worry about. So let's say to compute the limit of this guy, well, you can just consider the limit of the real part and the limit of the imaginary part. And turns out this guy should be tending to 0, and this guy should be tending to -1. So yeah, everything is just minus. All right. Also, this is also very obvious statement, but I will be using this statement very often in today's lecture. Suppose that I have a complex sequence that is tending to 0, and then this is the same as this. This is not a complex sequence. This is a sequence of real numbers, right? And it's the same as the sequence of real numbers is tending to 0. Okay, they are both identical, so they are also mathematically equivalent. So how can I prove this? Well, yeah, easy. Yes, I don't want to spend too much time explaining this. So you can, I believe you can prove this without too much trouble. Okay. So this is very clear. All right, so this is about the sequence. Now we are turning to the series. So what do you think is the difference between the sequence and the series? They are actually the same thing. The only names, the name is different, but actually the series terms, the convergence of series is defined by the convergence of the partial sum sequence. That was the definition that we studied in the freshman calculus course. And we're going to use the same thing for the complex sequence, complex series. I have a complex sequence. And this is an infinite series from n1 to infinity. So this is an infinite sum of the sequence. And so what do I mean by this infinite series converging to some number? To S if the sequence from K1 to N, Zk, so Z1 plus Z2, Zn. So this is not infinite sum, this is just finite sum. So as we did in the freshman calculus, so I'm going to call this guy as a partial sum sequence. So, and the convergence of an infinite series is defined by the convergence of this partial sum sequence converges to number S. In this case, we say one to infinity. So, well, also, well, if there is no such number S, then we say the series is divergent. If there is no such S, then we say the series diverges. Okay. Yeah, so there's no difference. It's same as the freshman calculus. And also, as you can expect, since the convergence of the infinite series is given by the definition of the convergence of the infinite series is given by the convergence of the partial sum sequence. Therefore, I can enjoy almost the same property as we did for the sequence. If suppose I have a sequence of complex number, which looks like this, x and whose real part is x and imaginary part is y, and say the S is large X times I times plus I times Y, then this infinite series converging to S if and only if the series of real part is converging to the real part of the S and the series of the imaginary part of Zn also converging to the imaginary part of the S. So these two things, these two statements, they are also mathematically equivalent. So, but this time, so I will not prove the statement. Why? Because, well, this is the same thing. Yeah, I can use the same trick from the previous statement. So, well, let us just take this for granted. So, therefore, since we now have this theorem, so therefore, the convergence of a complex sequence, the problem of the convergence of the complex sequence can be reduced to two different problems on the convergence of the series of real numbers. Okay. So, and this also gives me some idea. So, well, why? Because, well, so speaking of the convergence of the sequence of complex numbers, speaking of the convergence of the series of complex numbers, then, well, we actually need lots of tricks and techniques and theorems to do that. But, however, since the convergence of the series of complex numbers is nothing but the two convergences of the series of the real numbers, and for the series of real numbers, we had actually very interesting theorems like comparing theorems and limit comparing theorems, or the ratio test and root test, all those tests that you can remember. We can actually make uses of all these theorems without too much trouble, and we can apply all these theorems to the series of the complex numbers. Okay. Yeah. All right. So the proof is omitted. So the first corollary of the theorem is this, the so-called test for divergence. So let me try to remind you what the test for divergence was in the freshman calculus. So suppose that you are working on some series of real numbers, and there was a necessary but not the sufficient condition of the convergence of the series of real numbers. What was that? So if the summand, if the sequence AN is not tending to 0, then your series is automatically divergent, right? So that was test for divergence. And we actually have the exactly same trick for the sequence of series of complex numbers. Suppose that I have a series of complex numbers. And if this guy convergent, then this sequence Zn should be tending to 0. Okay, so why is it? Okay, let me say the Zn consisting of the real part Xn and the imaginary part Yn. And also we are assuming that this guy is convergent. Then, well, actually this is two-sided implication. So then Xn is convergent, and the series Yn is also convergent. And since these two guys are convergent, and now we are taking advantage of the test for divergence from the freshman calculus, then this guy should be tending to 0, and this guy should be tending to 0 too. So therefore, well, this is, well, because of our previous theorem. So I can split this in one sequence into these two, and this guy should be tending to 0. Okay. All right, so we have a test for divergence, just like we did from the calculus. All right, what's next? Well, do you remember, so when we were in the freshman calculus, so do you remember the notion of the absolute convergence? Well, yeah, so why we did do you remember the reason that we were working on we had the notion of the absolute convergence? Because, well, we had a test, well, comparison test or so-called the limit comparison test, these two tests were so useful, but however, these two tests were only for the series of positive numbers, right? And if you that means if your series has some terms which is negative values and which is sometimes positive value, then you may not be able to take advantage of the series, the test for the comparison test, these two nice tests. Okay, so in order to take advantage of these two very useful tests, so that is the reason that we needed a notion of the absolute convergence. And this is almost true for the series of the complex numbers. A series of complex numbers. Suppose I have this series is we say this guy be absolutely convergent if so you should be able to see the difference between this and that, this which is very obvious because this is a series of complex numbers. But however, on the other hand, this guy is what? This is a series of positive real numbers. Non-negative real numbers, right? And well, since this guy is non-negative real numbers, and we have so many tools and techniques in order to tell if this guy is convergent or divergent. And well, also there is a reason that we are studying the notion of the absolute convergence. Because if any series of complex numbers converges absolutely, then we are 100% sure that the series is also convergent. If a series of complex numbers converges absolutely, then this series of complex number is also convergent. All right, and I guess this requires just a little justification. Please allow me to say that Zn is xn plus I times yn, and also this is our hypothesis. So that means this guy is convergent. And in other words, this is just xn squared plus yn squared, and everything taken the square root. And this guy is convergent. Okay, oh, yeah, I'm done. And xn is, well, clearly less than the square root of xn squared plus yn squared. And yn is also less than equals to this. Oh, all right. So, okay, so this guy is less than this, and this guy is less than that. And also the series, this guy is also convergent. Therefore, now I can take advantage of the so-called comparison test from the freshman calculus. Comparison test. So this is convergent. This guy and this guy, they are both convergent. So you should remember these are real numbers, and the absolute values of these two series, they are both convergent. So therefore, these two series, without the absolute value, they are both convergent. Yeah, absolutely convergent. Yeah, but absolutely convergent means that they are convergent. Therefore, which is Zn is convergent. Okay. Yeah. So easy and nice. So there's not so well. All these analysis is actually they are actually in the high school level of high school, and so I can prove all these things without too much trouble. Okay. Now I want to talk about the remainders of a convergent series. Well, suppose that I have a series, then the nth remainder Rn is so z n plus 1 to z n plus 2. So the summation from the z n plus 1 to infinity, so these are defined to be a remainder of the series. So k is from n plus 1 to infinity of zk. So this is the nth remainder. And a series, and if this guy is convergent, then you know that this is mathematically equivalent to say that this remainder is, well, this remainder itself is a number depending on the index n, and this guy's convergent means that this remainder, the sequence of remainder, is tending to 0 as n goes to n to the infinity. If the series is converging to some number s, then, well, by definition, that means the partial sum sequence. So partial sum sequence is converging to s, but this is s minus. I should be saying the s minus sn 0, but this is Rn to 0. So, because of the reason, so, well, sometimes, well, if you want to show that some, well, series is converting to some number, then sometimes it is easier to consider the remainder of the series. And if you can show the remainder is tending to 0, and if you can express your remainder in very concise format, and if you can show that the remainder is tending to 0, then that means your series is convergent, right? Because, well, comparing the convergence of the series and convergence of sequence, I think, well, for psychological reasons, showing the convergence of the series is slightly easier than showing the convergence of the sequence. Sorry, I messed up. Showing the convergence of the sequence is easier than the convergence of the series. Okay. Okay, speaking of the remainder, let me try to show you that the convergence of the so-called geometric series. So you know what geometric series is. These were considered to be the one most important power series in the freshman calculus. And the same is true for the complex analysis. 1 over 1 minus z. So if and only if z is less than 1. So this is, well, this identity was true for the calculus, freshman calculus. And yeah, this is also true for the complex analysis. Let me show this. And first, so this is two-sided. So first, I will need to show that, so, well, the series is not convergent if the magnitude of the z is greater than or equals to 1. So if the magnitude of z is greater than or equals to 1, then what happens? Why is it divergent? Oh yeah, but which is very obvious, right? Because if this guy is greater than or equals to 1, then by the test for divergence, then this guy, z to the nth power, is never tending to 0. Therefore, yeah, should be divergent. Yeah. Series diverges because the test for divergence. Now, suppose that the z is less than or equals to 1, less than 1. Then I have 1 plus z squared to z to the n. Well, this identity, well, is still true for the complex analysis. Oh, sure. Z should be a number other than 1. So therefore, the partial sum sequence is 1 minus z to the n plus 1 and Sz is 1 over 1 minus z. Therefore, the remainder, which is the Sc minus Sn of z. So this is going to be just z to the n plus 1, everything over 1 minus z. And I am supposed to show that this guy is tending to 0. How? Well, yeah, I can try to prove this directly, but the easiest way should be just thinking of considering the magnitude of this number. Then this is just this guy, the magnitude of z to the n plus first power, and by the magnitude of 1 minus z. And since this guy is less than 1, and so we can still make use of the geometric sequence, the propositions from the geometric sequence, and this guy is tending to 0. So, and since the magnitude of this complex number, sequence of complex number, is tending to 0, that means Rn is still tending to 0. So, okay, great. So this is the geometric sequence. This is the geometric series. And what's next? Yeah, I feel like this course is more like the freshman calculus theory, freshman calculus. And the next theorem is about the comparison test. Suppose I have a series of complex numbers. This is given. And suppose that we can find a series, a convergent series of real numbers, a convergent series of real numbers. Such that the magnitude of Zn is bounded by Bn. No, sorry. or n, then Zn is converging absolutely. Okay, so this is the comparison test. Yeah, why? Oh, okay. So, well, do I actually need to prove this? No, not exactly, right? Because, well, if I have this nice inequality down there, then that means the series consisting of the magnitude of Zn. So, I mean, so you can just put the absolute value signs from here and there. Then the series consisting of the magnitude of these complex numbers Zn is converging automatically by the freshman calculus the comparison test. Therefore, this guy is also convergent. Okay. All right. So, and the comparison test itself is not that impressive, but we can actually use this theorem for just to prove the so-called ratio test. Suppose I have a series of complex numbers, and assume that these numbers, they are never zero. And suppose that this series is satisfying the following properties. Well, there is some positive integer n such that, so if index is greater than this integer n, and say that the ratio between two adjacent terms, Zn plus 1 over Zn, suppose that this number is bounded above by some number q, and we want this number to be strictly less than 1. Suppose that I can find such a nice number q over here. Then, for some q, then this original series of complex numbers converges absolutely. This is state number 1, and as you can expect, and this time around, I can find, suppose that I can find another complex of another integer, and if the index is greater than this integer n, and if the ratio between two consecutive, the ratio between two consecutive terms is greater than or equals to 1, then this guy diverges. Okay. So this is precisely the ratio test that we studied like long time ago. Okay, so let me try to prove this. Sorry. Okay, so number 1 and number 2, which one is easier? Yeah, I think number 2 is way easier than number 1. So I will try to prove number 1 first. Well, suppose that I have this inequality, then for sufficiently large index n indices n, and well, the magnitude of the Zn plus 1 is always greater than or equals to Zn. That means the magnitude of your complex number is getting large and large. And because of the test for divergence, this guy never be able to tending to 0, right? So therefore the series must be divergent. So, Okay. What about number 1? Okay, so for number 1, under this hypothesis, I must show that this guy converges absolutely. Okay. So if for the index greater than this large n, so I should have this inequality. So Zn plus 2 is greater than q times. Is it greater than, less than? Yeah, sorry, I messed up. Yeah. Z large n plus 1. Okay. So Zn plus 2 and Zn plus 1, but these, well, Zn plus 1 is clearly greater than n. So, well, therefore, I can make use of this inequality over here. So I have this inequality down there. And for Zn plus 3, yeah, by using the same trick, so is bounded above by Zn plus 2. But Zn plus 2 is also bounded by q times Zn plus 1. So this is q squared times Zn plus 1. Now I can clearly see the pattern going on here. So Zn plus k is bounded by q, is it k? Oh no, k minus 1, yeah, times the magnitude of Zn plus 1. Okay, so from k1 to infinity, so Zn plus k is bounded by 1 plus q plus q squared. So, and everything multiplied by Zn plus 1. Okay. And yes, this is good. And clearly, this guy is convergent. So this is a series of real numbers. And so also, you have to remember that we are assuming that this number q is strictly less than 1. So this geometric series must be some finite number. Therefore, this is convergent. All right. Okay, now what? So at this point, I have to take advantage of the comparison test. So by comparison test, n plus k is converging absolutely, right? Why? Because I was able to find a series of positive real numbers, and this series is also proven to be convergent. Therefore, this guy is also absolutely convergent. So this is also absolutely convergent. Okay. Okay, great. So there is a nice little corollary. I have a series of complex numbers, Zn, and suppose that the ratio of the two adjacent numbers, two adjacent terms, is tending to some number L. And if L is less than 1, well, I'm not going to spend too much time proving this. And if L is 1, then the series is converging absolutely. And if L is greater than 1, then the series diverges. And finally, if L is precisely 1, then I cannot say anything about the convergence or divergence of the given series in conclusive, in conclusive. Okay, so this is the root. So this is the ratio term. Well, actually, so we can actually make another theorem regarding the root test. So what is the root test? So suppose that I have series, and you may want to consider the limit of the magnitude of each of these terms raised by 1 over nth power. And suppose that this guy is tending to some certain number. And if this guy is greater than 1, then you can say that this is converges absolutely. And if this guy is greater than 1, then this guy is converging, this guy is divergent. And if this guy equals to 1, then you cannot say anything about the convergence or divergence of the series. Okay. Well, but however, this is exactly the same story. So, okay, I guess I am saying to just skip. All right. So, root test. Okay, now I am turning to the next section about the power series. I believe you are familiar with the real power series from the freshman calculus, and the complex power series is no different, the same thing. A complex power series is a series from n. The index is usually starting from 0, and an z minus z0 raised to the nth power. So this is complex power series, and as you may have guessed, so no different, the same. Well, also this number. So well, we said this number was center of the power series, and which is also true for the complex analysis. We are also going to call this guy the center of the power series. Then Z0 is the center of the power series, and AN is just They're just coefficient. Okay, so why do we even care about the power series? Okay, well, again, the same reason. So, well, I hope you can remember the first time that we have encountered the power series. So why we even care about the power series from the freshman calculus? Because, well, there are many interesting functions that can only be represented by a power series, right? So well, the series is just a just way to express some certain number. But power series is a way to express not just a single number, but the function. So, well, you also need to, you also need to consider this power series as a function of complex number z. Okay. And speaking of the power series, and speaking of function, the most natural question that arises when you're studying function is the number one, is it well defined? And number two, what is the domain of your function? So, well, translating in the word of power series, that means first thing that you will need to worry about the power series is what is for which value of z is this guy's convergent or divergent. So you need to find a collection of all such z's that make your power series convergent. So because of that, we will need to study the notion of the radius of the convergence. So number one. Okay, so given a power series, suppose that I have power series that looks like this. 0 to infinity, z minus z to the z. Then every power series converges at the center of the center. Oh, well, this is obvious because, well, if you plug in z equal to z0, then almost everything just goes to 0, except for the a0, right? So this is just, well, so this is just guaranteed. So there's nothing to prove here. And if suppose that my power series is convergent at z equals to z1. And let me say this number is different from the center of the power series. Well, because if z1 equals the center, well, then, so this is not very interesting. Then the power series converges absolutely for all z closer to the center of the power series than z1. So what does it mean? So, well, suppose that this is my complex plane. And let me say this is the center of the power series. Sorry. Well, and say that for some reason, suppose that I happen to find it happens to find that. Suppose that I somehow found that, well, if you plug in z equals to z1, then suppose that this guy turns out to be some convergent number. Then that means I should be a little bit careful drawing the circle. So that means okay. That means every point that is contained in this circle, not on the boundaries. For the boundaries, yeah, so I cannot guarantee for sure, but for all those numbers that is contained in this open circle centered at the z0, then for this point, I am pretty sure that if I plug in this for z equals to one of these points, then this guy is always convergent. Absolutely. Okay, so this is the meaning of the statement number 2. And for statement number 3, if the power series diverges at some point, then the power series diverges for all these whose distance from the center of the power series is farther than farther away from z0 than z2. So this means, well, now, okay, let me say that, so suppose that I just plugged in this point into this power series, and if this guy is not convergent, if this guy is divergent, then every point that lies not inside but outside of this circle so if you just randomly choose any point from this green shaded region and plug into your power series, then that makes your power series divergent. Okay, so number 1, the proof number 1, which is clear, and proof number 2. Yeah, this requires just a little bit of analysis. Well, suppose that, this is my power series, z minus z0 to the nth power. And if I plug in z equals to z1, and suppose that this, then because of our hypothesis, we know that this is convergent. Okay, then by the test for divergence, we know that this guy should be tending to 0. And any sequence of complex number tending to 0 is equivalent to say the sequence of real numbers consisting of the magnitudes of these complex numbers are also tending to 0. Also should be tends to 0, right? So here we are talking about not the sequence of complex numbers, but sequence of the real numbers. And you have to remember, so if there is any converging sequence, then the sequence must be also bounded. So you must be able to find some large possible real number m, such that all these guys should be less than or equal to that n, right? So this is bounded. So that means I must be able to find some positive real number m. So all these real numbers is less than or equals to this number n, right? Okay. So Now I want to consider the magnitude of this number. So this time this is not Z1, but just Z. But I guess I am good to rephrase this expression by Z minus Z0 to the N over Z1 minus Z0 N. And everything taken absolute value. Am I good? Yeah, this is good because, well, multiplying and dividing by same number doesn't change anything. So yeah, so I have this equality. But however, we know that this factor over here is bounded above by this positive real number m. So m times this guy. Yeah, sorry. I just changed my mind. This is n. This is, well, everything raised to the nth power. I just want to focus on this number. So for the numerator, so this means the distance between the point z from the center of the power series, and this is the distance from the point z1 from the center of the power series. So, and our assumption says that I have just picked my point z from this yellow circle, right? So therefore, comparing the distance between the z from z1, z0, and z1 from z0, clearly this guy, the denominator, is clearly bigger than the numerator, right? So this is inside of this parenthesis less than 1. So taking the summation of this is bounded above by m times z minus z0 over z1 minus z0 raised to the nth power. But you know, this is a clearly, this is a what? A geometric series. So this guy must be convergent. So the given series, given power series at z is absolutely convergent. Okay. Okay. Okay, this is the proof for number 2. And what about number 3? Yeah, I can easily prove number 3 because number 3 tells us that if I just pick any point from this green area, then that will make my power series divergent. Okay. So how can I prove that? Yeah, I can just prove this by using the proof by contradiction. Suppose that I was able to find some point from this green area that makes my power series convergent. Then, yeah, I can easily derive the contradiction because if this guy makes my power series convergent, then every point whose distance from the center of power series less than this point should make my power series convergent too. But because of a hypothesis, this guy, if I plug in this guy over here, then my power series is divergent, which is clearly contradiction, right? So yeah, so this is not horribly complicated argument. So yeah, I will just leave it like this. Okay, so so for power series, I have very well so what does this theorem mean? So this theorem means, well, I told you the reason that we are using the reason that we are interested in the power series is because we want to consider the power series as a function of z, right? And therefore, well, you should be able to consider the domain of your function. But however, because of the theorem, the domain of my function cannot be just any random slime living on the complex plane. So that means if your function is given by a power series, then your domain must be always some disk centered at the center, centered at the center of your power series. So, all right. So, and idea is I want to maximize the domain of my function given by power series. So that means, well, you can whenever you can find some point somewhere between this white area that makes your power series convergent, then that means you're actually increasing your domain of power series. But well, you cannot increase your domain forever because because of in this picture we know that this guy makes my power series divergent. So therefore the area of this circle, the maximum area of the circle cannot exceed over here, right? So this idea actually gives us the notion of the radius of convergence. I have a power series that looks like this. And suppose that there is a positive real number satisfying if the z distance of your z from the z center of the power series is less than this number, then my power series is convergent. And if distance from the center of power series is greater than this number, and my power series is divergent. Suppose that I can find such a positive real number R satisfying the condition number 1 and number 2. Then this number is called the radius of convergence of the power series. So, well, you should be able to remember that we also had the notion of the radius of convergence from the freshman calculus, and the same idea just carries over to complex analysis. On top of, sorry, and in my definition, so my radius of convergence is always supposed to be a number strictly greater than 0, right? But you can also say my radius of convergence equals to 0. What does it mean? So radius of convergence equals to 0 means, my power series diverges everywhere but the center. In that case, you say that, my power series has radius convergence equals to 0. On the other hand, if your power series is converging every complex number, z, then you can say, in that case, my radius of convergence is positive infinity. If the power series converges nowhere but the center, then we say the radius convergence is 0. And if my power series converges everywhere, then we say the radius of convergence is infinity. Okay, so this is the radius of convergence, and if I have a very nice way to find the radius of convergence, then that would be great. And do you remember? So how we found the radius of convergence from fractional calculus? We found the radius of convergence by the ratio test. And fortunately, we also have the ratio test in complex analysis. The ratio test is the best way to find the radius of convergence. So suppose that, sorry, my time's up. Yeah, I will leave it for my next lecture. And remember, there is no class on, so there is exam on the next class, and there is no class on the midterm week, okay? And I will see you on the Tuesday on the 9th week, okay? Great, thank you.